we're going to discuss orthogonal transformations and orthogonal matrices. But first, I would like to begin with the comment that I made at the end. So at the end of the last video, we were doing QR factorization. And I'm calling the matrix M instead of A just because I have A in the definition below. But we have a matrix, let's call it M, with linearly independent columns. And then, there exists this QR factorization where Q comes from Gram-Schmidt, right? And the columns of Q are orthonormal. And R was this upper triangular matrix that you could either fill in as you go along with Gram-Schmidt, or as I mentioned at the end, you can find R by taking Q transpose times M, well, on this side, right? So now let's actually define, although I defined it for Q, but generally for matrix A, this is where I'm starting today, we define the transpose. If you have a M by N matrix A, the transpose is a N by M matrix, whose ij entry is the ji entry of A. And this is what I said at the end, if you watched all the way to the end, where, for example, the rows of A become columns of A transpose. Similarly, the columns of A become rows of A transpose, and that's why you see these flipping. Okay. Now, so now let's put some more definitions. So a few more definitions, and then I will do some properties of the transpose. A matrix, and this is, let's see, here I need square. A square matrix is symmetric. This is what I'm defining. If, or provided, A transpose is A. And you see that you need square, right? Because the only time these are equal is if you have a square, or could be possibly equal, I would say. Definitely, it's not always the case. But it's symmetric if A transpose is A. The square matrix is what's called skew symmetric. If A transpose is negative A. Okay, so here are two definitions that are specific for square matrices, symmetric and skew symmetric. Here are two matrices. Now what I'm going to do is I'm going to verify some things for these two matrices, maybe over here, and then over here I'll write the general property. But it's good to see in an example. Okay, so what is one that I'm going to do? Well, let's take A transpose plus B transpose and see what we get. Let me switch markers. Okay, well, let's practice taking the transpose. Row 1 becomes column 1. Row 2 becomes column 2. This is A transpose. Okay, now row 1 becomes column 1. Row 2 becomes column 2. Okay, now we add. This is 3, 1, minus 2, 0. Okay, on the other hand, A plus B transpose. Let's do this. Well, first we add and then we transpose. You see, this is what I'm going to kind of do, is properties. But I'm showing them on these examples. Okay, if we add, we get 3 minus 2, 1, 0. And then I want to transpose. And, well, this row becomes this column, and this row becomes this column. And you see, in fact, these two are equal, and this is a property in general. As I mentioned, I'll write it over here. This holds, well, not just for square, and not just for 2 by 2, for example. This holds anytime A and B have the same size, such that you can add the two, okay? One thing I want to do is let's compute this, the product, AB, and then take the transpose. So let's do this here. I need to compute the product. Oh, maybe I'll just multiply, then I'll take the transpose, see what we get. Okay, well, this is 3 minus 1 minus 5 minus 1. Okay, that was matrix multiplication. The transpose is the new operation. So this row becomes this column, and then the second row becomes the second column. Now, what is this? Well, it is definitely not A transpose times B transpose. Maybe I'm going to erase some of this now to work on this new property that we're working on. Well, let's do that in this case. Why not? I have space. So it's important to understand what is a property and what's also not a property. So maybe I will do in blue. Let's do A transpose. Well, I just erased it. Okay, that's fine. Here's A transpose, and here is B transpose. Now let's multiply these two. We get and you see these are not equal. So maybe I should have put this A transpose times B transpose, and we get this. These two are not equal, so this is clearly not a property that works for all matrices such that the sizes work out. What is the property here, and we will verify it, is B transpose, A transpose. So the order flips here, it's not this one. Okay, so let's compute that here, and we should get this matrix, unless I've made a mistake somewhere. So B transpose we have written, I'll copy from above. A transpose I have written, I will copy from above. And now let's multiply these two matrices, and we get B minus 5 minus 1 minus 1. Okay, see, now this works. Of course, I haven't proved the property in general. I'm just verifying it on these small 2x2 matrices, and then I'm stating the property in general. But it's good to see some examples to understand the statement. So the property is that AB transpose equals, it's B transpose, A transpose. And this holds anytime the matrix product A times B is defined. Okay, now for the next one I want to do, and this is the last one that I'll do with these two examples, let me erase what I have so far. This one is only going to involve A. I will erase B for the rest of this because I'm not using it for the last property. Well, we know we did this several sections ago, how to find the inverse of a 2x2 matrix, right? Maybe I will recall this in red. If you have a 2x2 matrix, A, B, C, D, and you take the inverse, it's 1 over AD minus BC. And then you flip the main diagonal, this will become DA, and you take negatives of the off diagonal, minus B minus C. Oh, let me move that over. And this quantity here, AD minus BC, I called the determinant of the matrix, and I said we would return to it in chapter 6, and we will. Chapter 6 is not that far away now, but we're still not there yet. Okay, well, okay, so let's compute. What I'm going to compute here is I'm going to compute A inverse transpose, and I'm going to compute A transpose inverse, right? These are two different things. This is the transpose of the inverse matrix. This is the inverse of A transpose. So let's compute these two. And in part, doing this example, we understand that these are what these even mean, for instance. Okay, so this one says, first take the inverse and then take the transpose. So this is -2, so 1 over -2, and then you interchange what's on the diagonal, take negatives of what's on the off diagonal. Okay, but then transpose, right? Now, maybe before I transpose, let me bring this inside. This would be a half, this would be a half, this would be 0, this would be -1. And then I take the transpose. Okay, moving over here. Okay, well, this is a half, and then 0, -1. Okay, very nice. Now let's compute this way. So first we take A transpose. Okay, we have 2, 1, 0, -1. And then we take the inverse, which is going to be 1 over, okay, -2. And then you flip what's on the diagonal, take negatives of what's on the off diagonal, and then again I can bring the -1/2 in. I get 1/2, 1/2, 0, 1. Okay, and you see, -1, okay. 2 times -1/2 is -1. I was like, oh no, it's not working. Okay, now we see the property. Right, these are equal. So the property that we see here is, if you want, well, I could write it either way. A transpose inverse is A inverse transpose. Now this third one, of course, this is provided A is invertible. Because otherwise A inverse doesn't even make sense. But another thing that's interesting from here is we see, for instance, an n by n matrix. If you're invertible, well then so is the transpose. I will add over here, if you have a matrix, you take its transpose, and then you take the transpose of that, you get back the matrix. Why would this be the case? Well, let's think about the ij entry here. Okay, well, it would be the ji entry of A transpose, which is the ij entry of A. Okay, so the ij entry of this matrix is the same as the ij entry of that one, and we get they're equal. You could also just think, if you interchange rows and columns and then you interchange rows and columns again, you get back the original matrix. Now, let me say one more here, and then I might erase and say or make a comment that we'll spend more time on. But one more I'll mention here is that the rank of A is the same thing as the rank of A transpose. And you know, this you don't need square. So the only one you need square for is this one. You need square just because we don't speak about A inverse if you're not square, and you also, well, need invertible, but the other ones you don't need square. These two you need the operations to be defined. These two work for any matrix A, okay? Okay, so these are some nice properties, and we saw a couple of them for some 2x2s. But now what I'd like to do is say something more that connects back to the sort of theme of this chapter, which is orthonormal bases. Okay, so this property is great, super important, and adds another heart to our we love orthonormal bases. Okay, if we have an n by n matrix, so it's square, the columns form an orthonormal basis for Rn if and only if A transpose A is the identity. And well, we know this red part, the if and only if, these two are without a doubt equivalent. This we discussed in our matrix inverse section, that anytime you have an n by n matrix, such that you multiply on one side and get the identity, automatically that matrix is the inverse. And this is here. This is the identity, n by n identity. And this is important that everything is square, because we saw at the end of last time, my argument was that Q transpose Q, when Q was not square, was the identity, but without a doubt, well, Q is not even invertible because it's not square. And I'm going to come back to that at the very end of today. So we kind of ended with it last time, and we're going to end with it again this time. But right now, I'm just focused on square matrix. Okay, well, my proof of this is very much like my discussion at the end of the video, but let's do it carefully. But before I do, so first, before I discuss this, let's just discuss vectors in Rn. And I touched on this last time, but I will mention it a little more today. For a vector, and you know, typically we think of a vector, maybe I don't need to write the word vector, I'll just do this. We write a vector as a column vector. This we discussed at the very beginning, that typically we think of vectors as columns unless otherwise noted or implied or something like this. So let's think about a vector like this. Well then, the transpose is a row, right? It's a row. Okay, so if we go back, and this is almost the first week of class, probably the first week of class, how do we define dot product? And you remember, if I want to take, let's say, V dot W, the way that I wrote that at the beginning even was like this. We have some V1, V2 to Vn, and then I wrote it like this. 1, W2 to Wn. And I remember, because I kept talking about this motion that we use and when we multiply matrices. Okay, but what we see here is we can write this in terms of just a product of matrices, really. It is V transpose W. And the good or important observation that we need to make from this is this, as we know, maybe I'll do this in red. This is the dot product, okay? But when we write it like this, it's really thinking about it as like a matrix product. Just writing it multiplied, V transpose times W, just like you would write multiplying two matrices next to each other. And thinking about it like this is actually going to be quite important for some things that we do. Okay. But I wanted to make that comment before I get into this. Okay, very nice. Now I'm going to erase because I want to talk about this matrix A. Okay, I'm going to leave out, this was my side comment to talk about the dot product because it was important. Okay, but now back to this. Okay, so let's suppose we know A is n by n. And this is really an if and only if. And A is, I need some columns, let's say V1, V2 to Vn. These are, each one of these is a vector in Rn because our matrix is square, okay? Okay, then, A transpose, well, we know what happens. You just, every column of A becomes a row of A transpose. But really they're rows. So I'm going to write them this way. And this is really the appropriate way to think about them. Okay. And, oh, maybe I should have left that space because I was going to do these. These are rows. Okay, so now let's compute A transpose A. And A transpose A is, well, I just recopy, it's this down to VN, transpose. I started to put the wrong thing. And then, maybe I'll use this color here. And this is a very similar observation that I made at the end of last time. So what's happening here? Look, how do you multiply two matrices? Row, column, row, column. But I will just write it like this, that the ij entry is vi dot vj. Okay, we've represented matrices like this before. We put brackets and then we just write the little ij entry in here. So the ij entry of this product is vi dot vj, right? We can see. And so far, this is just calculation, but now I have an if and only if. And so this matrix, vi dot vj equals the n by n identity, if and only if, well, vi dot vj equals 1 if I equals j, and 0 if I not equal to j. And this is the case if and only if, well, the columns, this collection is orthonormal. But more, I'll just say orthonormal basis for Rn. Well, why can I say all that other stuff? So this part says they're orthonormal. We know a collection of orthonormal vectors is linearly independent. We know any linearly independent collection of n vectors in Rn is a basis for Rn. Okay, so in fact, just having this and the fact that there are n of them, we get that they're orthonormal basis for Rn. Okay, now, this is very nice. It says something about, well, we know just by taking the transpose, we have the inverse. If you have a matrix where the columns, n by n matrix where the columns are orthonormal. Now I should add right now, so this is called an orthogonal matrix, but our text uses a different definition of orthogonal, and then for a matrix, it's not that the columns form an orthonormal basis for Rn, and then proves that's equivalent to this. So I'm just going to say right now, this will be an orthogonal matrix when the columns, when it's square, and the columns are orthonormal. But if you just wait a few moments, you'll see the definition. I'd like to discuss a theorem that comes up from this. Well, let's suppose A and B are square n by n matrices with orthonormal columns. And this is just a short way to say that the columns of A and similarly the columns of B are orthonormal bases for Rn. Okay, then, well, the columns of A inverse are orthonormal bases for Rn. It's the same thing as this, because A inverse is also n by n square. And similarly, the columns of A times B are orthonormal. This is also n by n square, so we would have that they're also a basis for Rn, orthonormal basis, for example. Okay, but what I'm really going to use is this characterization of being a square matrix with orthonormal columns. So maybe I will prove 2, because I think it's a lot more enlightening, although maybe I'll prove 1 also. We will have to see. But let's prove 2. So what I would like, so we assume that A, B are n by n with A transpose A is the identity. This is the n by n identity. And B transpose B is the n by n identity. And we need to show this AB transpose times AB is the identity. Right? Because this is equivalent. This was what we just discussed. Is equivalent to the columns of this matrix being an orthonormal basis for Rn, or saying this, knowing you have n of them. Okay, well now we just use properties of transpose. So we have the following. If you take the transpose here, we discussed this property. It's a transpose of a product. This is B transpose, A transpose, and then I have AB. Now, you notice I didn't put my parentheses anymore because you can multiply matrices. Well, you cannot necessarily change the order this way, but you can group them however you want. It's the associativity of matrix multiplication, which means I can multiply first A transpose A on the inside, and I get the n by n identity. And then, well, maybe I'll move here. Identity times anything is just itself. So now I have B transpose B, but again, this is the identity. So what we showed is that this product, A times B, satisfies this, and by the if and only if theorem we just discussed, this also must have orthonormal columns. Okay. Uh-oh, this was number 2. Sorry about that. Now, what I'd like to do at this point is go back to transformations and go back to a little bit about geometry even, and I will tell you the definition of an orthogonal matrix as in our text, but then we will see, and not very long, that it's the same thing as what I've been just stating it was, which is that you have the n by n matrix and the columns are orthonormal, or equivalently, they're an orthonormal basis for Rn. So let's start with a definition about transformations, because we're moving back to transformations. If you have T from Rn to Rn, and this is a linear transformation, T is orthogonal. So this is now, okay, you should be excited because this is the title of this section, right? T is orthogonal. It's called orthogonal transformations and matrices. And we've seen some things which I will connect to the orthogonal matrices. But here we go, okay? It's orthogonal provided the length of T of x equals the length of x for every x in Rn. So what this says in words is that T preserves lengths. I'll write it, because we're going to see some other things that T preserves if it's orthogonal in today's lesson. T preserves lengths. This is what this definition says. And then the definition, and n by n matrix A is called orthogonal provided the transformation T of x, which is AX, is orthogonal. So this is the definition of orthogonal matrix. I can unravel it even more. So in other words, the length of AX equals the length of x for all x in Rn. We will see that this is equivalent to the columns being orthonormal. Okay. What I'd like to do now is just, if you remember from chapter 2, linear transformations and geometry, we looked at pictures, well, in Maple, and tried to see geometrically what was happening. We had rotation, reflection, the projection on a line, scaling and shearing, and I just wanted to look at those, some of them, and see which of these are orthogonal transformations and which are not. Okay, so here, well, if we look here, what I'm going to do is I'm going to have this standard L, and then we're just going to look at what happens out of the transformation, but we'll also think about what's happening to figure out if it's preserving lengths. Well, what's this first matrix? Well, what do we see? We see square root 2 over 2, square root 2 over 2. Okay, this is a cosine theta, sine theta, minus sine theta, cosine theta. This matrix is rotation, or the transformation gives rotation counterclockwise by an angle of pi over 4. Okay, well, what do you think? I should say the pictures can be a little deceiving, but here is rotation counterclockwise by pi over 4. Now, exactly what happened is, okay, okay, here we go. Here we are. Now, I don't know if it's, if you're seeing my mirror or not, so just pretend, whichever direction I go, pretend it's counterclockwise. Okay. But you see what rotation does, even though you rotate it back, okay? Rotation is not changing lengths at all, right? You're just rotating. So this is, well, it's an orthogonal transformation, the rotation for any angle theta. Now, what else would be? Well, one example is a reflection. And we saw one if we did 0, 1, and then here was 1, 0. This gave us reflection. 0. This reflected about the line y equals x, right? This was in our very first day talking about linear transformations. But any kind of reflection, you're preserving the lengths. But what does not? Okay, well, scaling does not. This should be pretty clear. Let's do this. This is the one where I said these pictures can be deceiving. We see it in the scaling because if you look, did I do the second one? It looks the same until you realize that this goes to 10 and this goes to 5, whereas they were 1 and 2. So this, without a doubt, does not preserve lengths. But another one that does not is orthogonal projection. Okay, so make sure, orthogonal projection, this is something, and we have discussed. Orthogonal transformation, this is something, and we are discussing now. But orthogonal projection is in fact not an orthogonal transformation. Okay, this is the beauty of math. Okay, because it does not preserve lengths. Well, the easiest example to realize that orthogonal projection is in fact not an orthogonal transformation is just looking at this matrix here. Well, maybe I'll show you what it's doing. Here's what it did. This matrix projects to the x-axis. And you could even see that if you think about the formula, if your unit vector on the line is just 1, 0, and so you would take u1 squared, that's the 1, and then u2 squared, 0, and then u1 times u2 is the off diagonals, and those are both 0. So without a doubt, this matrix, it projects down to the x-axis, and you see, if you project, you may not see it here, but if you project this second vector down to the x-axis, v2 as it's called here, it's 0, okay? and the length of 0 is 0, not 2. So this does not preserve lengths. Orthogonal projection, generally, it is not an orthogonal transformation. Okay. Well, I want to discuss this theorem here, which is a really, so this is a theorem, okay, which is a really important part of orthogonal transformations, and it's as follows. If T is an orthogonal transformation and U, V are orthonormal, then T of U and T of V are orthonormal. Well, let's think about this for a second. There's two things to being orthonormal. These two vectors are orthonormal provided they're both unit, and then their dot product needs to be 0. Okay, well, why are they unit? That I will mention first. We know the length. This is definition. The length of T of U is the length of U, which is 1, and also similarly for the length of T of V is the length of V, which is 1. That's our assumption that U and V are orthonormal. The next part is that they are perpendicular. I will just use this word because I already have orthogonal on the board talking about the transformation. So why are T of U and T of V perpendicular? Well, let's go back, and I think I had this on not the last video, but the video before, of a characterization of perpendicular vectors, but it's really just the Pythagorean theorem. Okay. Okay, here's T of U. Uh-oh. And then here's T of V. And then this is just vector addition. This black vector is T of U plus T of V. Now, what I need, if this is a right angle, this is what I need to show, or what I need is that this length squared T of U plus T of V, this length squared, that's the hypotenuse. It needs to be equal to this T of U squared plus this length T of V squared. This is equivalent to this vector and this vector being perpendicular. Okay, well, let's work with this. So we have, this is the picture, we have, I'm just going to work with the left-hand side. This length, T of U plus T of V equals, no, maybe I got a better black, maybe I will use this. Well, first of all, it's a linear transformation. So T of, squared, I forgot it. Maybe I should keep the squared in blue. Squared. Okay. Now, it's a linear transformation, so T of U plus T of V is simply T of U plus V. Okay? But now, this, well, T preserves lengths. So T of U plus V, its length, is the same thing as the length of U plus V. And same for squared, right? If you have two numbers that are equal, you square them, they're equal. So this length squared is equal to this squared because T is orthogonal. That's this one. And the one above, well, I don't have room to write it, but I mention it's because T is a linear transformation. That was this property. Well, now, this is equal to this squared plus this squared. Maybe I'll put my, because U and V are perpendicular. These were assumed to be, oh, it's little. These were assumed to be orthonormal, so they're perpendicular vectors. And then I'm going to use one more time that T is orthogonal, that this length squared is equal to T of U squared, and this length squared is equal to T of V squared, okay? And this again as T is orthogonal. So what we see from this is when we have an orthogonal transformation, that it maps orthonormal vectors to orthonormal vectors. Certainly, these would all be orthonormal because the standard vectors E1 through En is an orthonormal collection, and so T of all of those would be an orthonormal collection. Okay, but this is an if and only if, that this having these vectors all map to, or all be, I should say, an orthonormal collection is equivalent to T being an orthogonal transformation. I could also, let's see, I could change this, and I think I might have said this, an orthonormal, I can say basis for Rn, because we have n of them, right? And I've even discussed that some in this video. If you have an orthonormal set of n vectors in Rn, automatically it's an orthonormal basis. Now what do I want to say next? Oh yes, we want to go back to the matrix, because look, this is if and only if the matrix for T, which is, we know the matrix, it's this. A is T of E1, T of E2, out to T of En, and we practice calculating some of these, right? Where you put, how do you find the matrix for a transformation? Well, you evaluate T of each of these, put them as columns, then you have the matrix. So if and only if the matrix for TA has orthonormal columns. So in other words, A is an orthogonal matrix if and only if the columns of A form an orthonormal basis for Rn. And this is why I refer to this. I was working with A's that had orthonormal columns n by n, and this means that the columns are an orthonormal basis for Rn, and I just said that that was orthogonal, and I said we'd come back and see it later. Really, the definition of orthogonal is that the matrix is associated to a transformation that preserves lengths. But from what we just proved before this and this discussion, a matrix being orthogonal is equivalent to its columns being an orthonormal basis for Rn, and this only happens for square matrices. What I want to discuss is another property of orthonormal, let's say, transformations. Every property I could write as either a property of the matrix or the transformation, but this one I want to write in terms of the transformation, but then I'll use the matrix also, okay? So suppose we have T, Rn to Rn, orthonormal, and I will spell out the matrix here because I'm going to use it. T of x is A times x. Okay, so what I want to say, and I'll write it in words and then I'll state it, is that we talked about T preserves lengths. In fact, that's the definition of T being an orthogonal transformation. What I'm going to say now is T preserves dot product. So these orthogonal transformations preserve a lot of things. They preserve length, they preserve dot products. You will show in the homework they preserve angle, but I will say a lot, you can use what I have shown here to show that they preserve angle. But how am I going to show they preserve dot product? Okay, well what I want, let's write this. What we want here is that T of x dot T of y equals x dot y, and this is for all x, y, and Rn. This is what it means to preserve dot product. Okay, how am I going to do this? Well, I'm going to use the matrix. T of x dot T of y. This equals ax dot ay. But now, you see, I spent a lot of time with matrices at the start because that's really the way I think about transformations, and it's really the way that I wrap my brain around linear, of course, transformation. So remember, what was this dot product? If you can write it as follows, ax transpose ay. This is writing a dot product as a matrix product, right? But then we can use properties of transpose, properties of the fact that A is an orthogonal matrix. Okay, here we go. This will be fun. This is X transpose, A transpose, and then here we have A, Y. Look, but A is orthogonal. I'll even write that where A, by definition, is an orthogonal matrix. I left off some words. Letters, I mean. Matrix. That's the definition, but we know that's equivalent to the columns of A forming a basis for Rn, and is equivalent to, by what we talked about at the start of today, that A transpose A is the n by n identity. So look, this in the middle here is the n by n identity. So this is X transpose times the identity. Oh, I need my hats. Okay, I think I'm okay now. Okay, well, identity times y is y. We get X transpose y, and this is X dot y. Okay, so we see that this T preserves dot product. Okay, so this is, like I mentioned, it's a really great property of orthogonal transformations. Now, I have one more super cool thing to talk about. I mentioned we were going to end today on the same note that we ended the last video. So here we go. So recall, at the end of the last video, we had Q, which we got through Gram-Schmidt, okay, which means it has orthonormal columns, but it was not square. In fact, what I'm going to say is important for not being square. So Q would be n by m, and, well, in order for the columns, m of them, to be independent, we need m strictly less than n. Okay, I'm not talking about square ones. If it's square, we know what's going on. It's an orthogonal matrix, and the transpose is the inverse, right? But I'm talking about the non-square matrices with orthonormal columns, and I showed in a very similar way to how I showed for square matrices today that Q transpose Q was the identity. Now I have to think about the size. Q is n by m. Uh-oh, I did it backwards. This one, n by m. This one's m by n, and this one's this identity. It's the smaller identity. And if you remember, this is something that has come up this semester. Q transpose here is called a left inverse. But it is without a doubt not an inverse because Q is not square. Now, the question is, and this is what I want to talk about right now, which is super cool. The question, I'll do it in blue. I'm excited to share this with you because it relates last time and things we have discussed today. The question is, what is this? Q transpose. What is it? Well, first of all, we know its size. This is the bigger one, n by m, m by n. It is not the identity. So answer number one, in fact, that was sort of a comment that I made in one of the videos. So I had two videos where I mentioned a left inverse before, and we did similar things. Without a doubt, this is not the identity. So answer number one, it's not the identity. Cannot be. Oh, not the identity. Not a chance. Not if m is less than n. Okay. Well, but what now? This is answer one. So let's finish. The answer number two is very neat. Q has orthonormal columns. Now, this is going to be confusing. I should write question because it looks like the same as my matrix. Q has orthonormal columns. We were calling them U1, U2 to UM. Okay? To figure out this matrix, QQ transpose, we will just see what happens when I multiply by an x in our n. Okay, so Q transpose times x. What is this? Well, Q is here with columns, and Q's transpose, I know the rows. Oh, transpose, out to UM, transpose, like this, and then X. Now, the neat thing about the observation we're going to make is we have to think about both ways of multiplying a matrix. We have to think about the row picture, and we have to think about the column picture. So the first thing I'm going to do is I'm going to think about this, Q transpose X, in terms of row.x, 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 like this. So right now I am recopying Q. Okay, and then, then this will be the product. I'll write it as a dot product, U1 dot X, okay? This is a vector, right? So I don't need the transpose anymore. You take row dot this, it's a number. So this, I meant, is a vector. And then this entry is U2 dot X all the way out to UM dot X. So far, so good. Well, now I have one matrix, this one. In fact, I can make it clear. Matrix, vector, matrix, and this is matrix 2. Okay. So I have one more matrix times this vector to figure out what this Q transpose is, and this is where we see how cool this is. I'll do it right here. Okay, well, this is when I'm going to think about the matrix times a vector as a linear combination of columns. Here are the columns of this matrix, so I can write this as U1 dot X, U1 plus U2 dot X, U2 plus UM dot X, UM. Now, stare at that for 2 seconds after having done the homework for the last section, especially. What do you see? Orthogonal projection. So what you see here, this matrix, QQ transpose, is projecting onto, right? This is the projection formula. It's projecting onto the subspace spanned by U1 through UM. And this is the matrix of orthogonal projection. Okay, so this is, I'll make it as a comment below. So this is very cool. This Q transpose is the matrix for orthogonal projection onto the subspace, which is the span of the UIs, U1 to UM, on this m-dimensional subspace of Rn. Okay, so this is something that is, well, neat to think about, and this is why I said that order really matters when we were using Q transpose times the matrix to find the R in the QR factorization, because you multiply Q and Q transpose in one way, you get the identity. Multiply them the other way, and you get the matrix for projection, which is, well, it's definitely not the identity, well, for example. But, okay, so this is about when Q is not square, but the columns are orthonormal. And then we will close with the following comment. I want to end with this summary. This is from our textbook. For an n by n matrix, these are all different ways of viewing or thinking about A being orthogonal. And I started with 3, that the columns form an orthonormal basis for Rn, because it naturally came from, at least in my opinion, what we were discussing last time. And then we showed that this is equivalent to A transpose A being the identity, equivalent to A inverse equals A transpose. And then there's this transformation that was multiplying by A, and the definition of orthogonal matrix is that this transformation, they call it L here, but that it preserves length. So the length of A times X is the length of X for all X in Rn. And then the last one, this 6, this we also proved that A preserves dot products. Okay, so I wanted to close on this. It's all equivalent to saying A is an orthogonal matrix, n by n orthogonal matrix.